Have you ever just stopped and wondered how on earth developers build the massive, complex software we use every single day? Without it all just collapsing into a tangled mess? I mean, how do you write millions of lines of code that are secure, reusable, and easy to update? Well, let's get into it because the answer is a pretty brilliant way of thinking called object-oriented programming. So to really appreciate why OOP is such a game changer, you gotta understand the problem it was trying to solve. Back in the early days of programming, the bigger a program got, the more chaotic it became. We're talking a giant web of functions and data all tangled together. Imagine trying to fix one tiny bug and accidentally breaking 10 other things. Seriously, it was a total maintenance nightmare. Something had to change. And when you put the old way next to the new way, it's a night and day difference. The old structural programming was very top-down, and data could just kind of flow everywhere. That is a massive security risk. And changing anything, super, super difficult. OOP just flips that whole script. It takes a bottom-up approach, building secure, flexible components from the very start.
So what was this new way? Well, it was all about structuring programs around, objects. The idea was honestly revolutionary. What if we modeled our software to act like things in the real world? A car, a student, a bank account? Each object would hold its own information and know how to do its own tasks. It brings a real sense of order to all that chaos.
So how do you actually make one of these objects? You start with something called a class. And honestly, the best way to think of a class is as a blueprint. If you're going to build a house, you need the plans first, right? The blueprint defines everything a house should have. Rooms, a kitchen, a roof, but it's not the house itself, it's just the plan. Okay, so if the class is the blueprint, then the object is the actual house you build from it. It's the real thing, the instance you can see and interact with. And the cool part is you can use that one blueprint to build tons of unique houses. Each one is its own object. One might be painted blue, another red, but they both came from that exact same master plan. And you can see how this plays out right in the code. It's actually pretty straightforward. Here, student is our class, that's the blueprint. Then with that simple line, student1 equals new student, boom, we've created a real individual student1 object. We've literally brought our blueprint to life.
Now, what's the secret sauce that makes all of this work so well? Well, it all rests on 4 fundamental principles. People call them the 4 pillars of OOP, and they are the foundation that gives this whole paradigm its power and its elegance. If you can get these, you can get everything else.
First up, we've got encapsulation. This is all about bundling data and the functions that work on that data into one nice, neat little package. Think about your car's dashboard. All the super complex stuff happening in the engine is encapsulated. It's hidden away. You, the driver, you just get a simple speedometer. This protects the engine's guts and stops you from accidentally messing something important up.
Next is abstraction, and it goes hand in hand with encapsulation. Abstraction is all about hiding the messy reality and only showing what's essential. For example, when you hit the gas pedal, you don't need to understand the physics of internal combustion, right? You just need to know that pedal down makes the car go faster. And that's abstraction in a nutshell, making complex things simple by hiding all the details you don't need to worry about.
Our third pillar is inheritance, and this one is all about being efficient and reusing your work. Let's say you have a general blueprint for a car. Now, if you want to make a sports car, you don't start from scratch. A sports car is still a type of car, so it can inherit all the basic stuff, wheels, an engine, you name it. Then you only have to add the special features, like a turbocharger. It saves so much time and stops you from writing the same code over and over.
And finally, we have polymorphism. Now, this one sounds super complicated, but the name literally just means many forms. It's the idea that a single command can have totally different outcomes depending on the object it's acting on. So if you tell a car object to start engine, it might make a vroom sound. But if you tell a bus object to do that exact same start engine command, it might make a loud rumble. Same action, completely different behaviors. And just to dig in a tiny bit deeper, polymorphism really comes in two main flavors. You've got compile time, where the program figures out what to do as it's being built, and then you have runtime, where it makes the decision on the fly as the program is actually running. That dynamic runtime version, it's incredibly powerful, especially when you combine it with inheritance.
Okay, so we've talked about these 4 pillars: encapsulation, abstraction, all that stuff. But why should you care? How does all this theory actually translate into the real world? Well, as it turns out, this way of thinking is pretty much the backbone of almost all the software you use today.
And I mean, pretty much all of it. Just look at this list. These are the absolute titans of the programming world. You've got Java running huge enterprise systems, Python powering data science, JavaScript running basically the entire web, and all of them are built on the object-oriented principles we've just been talking about. Its influence is just massive. So the advantages really tie directly back to our 4 pillars. That idea of inheritance, that gives us amazing code reusability. Encapsulation, that makes our code way easier to maintain and, really importantly, much more secure because it protects our data. It all adds up to building big, complex systems faster and more reliably. But of course, it's not a silver bullet. Nothing is. This approach takes a lot of careful planning, it's a different way of thinking, and for really small, simple problems, it can actually be overkill, making your programs bigger than they need to be. Look, OOP is an incredibly powerful tool, but a great developer knows it's not the only tool, and the real skill is knowing when to use it. So once you learn these 4 pillars, you really have a powerful framework for building clean, solid code. But, and this is the exciting part, it's really just the beginning. It's like a gateway to a much deeper understanding of how truly great software is designed.
And this is where the path goes next. Once these pillars are like second nature to you, you can start exploring even more powerful ideas. You'll run into things like solid principles and design patterns, which are basically proven recipes for solving common programming challenges. It's a journey of learning that, honestly, never really ends.
Which brings us to one final, kind of fascinating thought to leave you with. We use object-oriented programming to build these clean, elegant models of our complex world inside a computer. But what happens when the real world is messy, unpredictable, and just way more complex than the neat little models we build? Well, figuring that out, that's the challenge, and really the art of modern software development.